Let's talk about saturation. That is our next topic. So we've already talked a little bit about what solutions are, how it's usually solids dissolve in liquids, but there's lots of other kinds of solutions. And we talked a little bit about soluble versus insoluble. So technically speaking, every compound is at least a little tiny bit soluble. We go way into that more in AP chemistry. It's a much bigger topic. But even the most soluble compound has a limit. And it's the saturation. How much of this solid can you actually dissolve in a certain amount of liquid? And there comes a point when you just can't get more solid to dissolve in liquid, and it will all fall out or precipitate out of solution. So remember, precipitate means comes out of solution. So let's take a look at some examples of this. I'm actually going to use a POGLE to give you some really good visuals. You don't necessarily have to do the POGLE, but I did give it to you in your printouts. Let's take a look at the definitions first, and then we'll go to the visuals. So a saturation is how much you can possibly dissolve. An unsaturated solution is a solution where you have less solute than possible, and you could still add more. A saturated solution is exactly at that point. You cannot add any more without precipitation. And a supersaturated solution means that there's more than you possible to dissolve. And either it's going to stay in solution, but very precariously, or it's all going to begin to fall out of solution and precipitate. So there's a really nice illustration of this here, and I'm going to draw a similar picture for our notes. But we have this beaker. They all contain 10 grams of water, and it looks like they just kind of keep adding more of this solute. So they start off with 1 gram of solute, and then 2 grams of solute, still dissolved, no problem. 3.6 grams of solute, but now we're at 7, and suddenly the solid is starting to accumulate at the bottom. And after you add 2 more grams, it just looks like all of it, none of it really dissolves. So this is a great example. Our saturation point is probably here. We're not really sure. It's somewhere between these 2 points, somewhere between 3.6 and 7. These are unsaturated solutions, and these are both supersaturated. There's too much in there. It cannot dissolve anymore. So that's kind of a good visual of what this definition is. So let's draw our own little picture, our own picture of what that means. So I'm going to have 3 examples here. The wavy lines, as always, represent water. They're blue. So let's do unsaturated, saturated, and supersaturated. Okay. So an unsaturated solution has a fairly low concentration. A saturated solution everything is still dissolved, and at a supersaturated solution, not everything can dissolve. Okay, so that's the kind of idea behind that. This comes up in your life a lot with cooking, especially with baking. Some great examples of supersaturated solutions are if you are making iced tea. It's really hard to dissolve iced tea, sugar into iced tea when it's cold, but you can make a really sweet tea, like Southern sweet tea. If you boil the tea first, and while the water's still hot, you can dissolve in a lot of water, and then as it cools, it's technically a supersaturated solution. Oh, I should write this down. It just reminded me. Saturation is temperature dependent. Generally speaking, saturation increases with temperature, which you kind of know, from that exact situation. You can dissolve a lot of sugar in hot water very quickly. It takes a lot longer with cold. That's also how you make fudge. Fudge is a supersaturated solution to get lots and lots of sugar in there. Same thing with simple syrups that you would use for possibly in coffee shops. All the simple syrups are just sugar that is dissolved in water up to the point where it's really probably shouldn't be dissolved anymore. But because you did it while it was hot, it managed to stay in solution. Okay, I think that's the main things I need to say about it. Let's talk about the packet. Yeah, I think it's time to go into the packet. So taking a look at the packet, you are going to see a solubility curve. So we're going to be working on pages 4 and 5 and 6, and they all refer to this one graph. This is called a solubility curve. So let's figure out what's up with this. A solubility curve shows how many grams of a specific substance can dissolve in 100 grams of water at specific temperatures. So if we take sodium nitrate, for example, at lower temperatures, fewer grams will dissolve, but they still will. At 0 degrees Celsius, you can still get, I don't know, what is that, like 73 grams of sodium nitrate will dissolve in 100 grams of water. As you increase the temperature, that amount goes up. So by the time you get to 85 degrees Celsius, 150 grams, you have pretty much doubled the amount that will dissolve. That's pretty cool. And each of these curves represents something different. Most of them, the general trend here is that as you increase temperature, solubility increases. Even sodium chloride here, it's pretty subtle, but there you go. There's a few exceptions. Ammonia seems to decrease. So colder temperatures seem to be better than higher. Same thing with this cesium sulfate. So those are a couple of weird exceptions, but mostly that's not the rule. So let's answer some questions and we'll see what happens. Okay, a couple of notes. 100 grams of water is also 100 milliliters of water. I just saw something come up with that in one of these questions. So as you go through these questions, at 30 degrees Celsius, approximately 10 grams of potassium chlorate will dissolve in 100 grams of water. Let's see if that's true. Potassium, yep, that looks about right. If the temperature is increased to 80 degrees, approximately blank of the substance will dissolve in 100 grams or 100 milliliters. So we went up to 80. So we have to follow this particular line to 80, and it looks like we are now looking at 40. So if you see potassium chlorate right here, so that point goes to 40. Sorry, there you go, now you can see it. Okay, so that's how we got the answer of 40 there. All right, and it's 40 grams, sorry, 40 grams of the substance will dissolve in 100 grams of water. All right. If you reduce the amount of water, that will be directly proportional to the amount of grams that will dissolve as well. Okay, so let's look at one more of these, and we'll hopefully then you can do the rest. How about for potassium nitrate at 70? So we need to find 70 degrees. We need to find the potassium nitrate curve, which is here. We just need to follow until they meet. Looks like they meet right about here, and that's at about 130 grams. So our answer would be 130 grams. It's not dissimilar to the pressure volume, the pressure and temperature graphs for phase changes, but it also isn't. It's also actually not that much like it. It's sort of. This is kind of like a phase change between dissolving and not dissolving. So that means what that really means here is that if you tried to dissolve 140 grams, it would not be a saturated solution. It would be a supersaturated solution. If you tried to dissolve 120 grams, it would dissolve easily and it would not be saturated. So this line basically says, what is the saturation point? So the solubility curves are for saturation points. So instead of boiling point or melting point, it's like a saturation point. So in a lot of ways, it is kind of like a phase diagram. Okay, let's go to page 5 and we'll pick out another problem or two. Okay, how about this block here? So we need to figure out if these are unsaturated or saturated and how much more could we dissolve. So let's start with 70 grams of sodium nitrate at 30 degrees Celsius in 100 milliliters of water. So 30 degrees Celsius sodium nitrate. 30 degrees Celsius sodium nitrate. Sorry, so you can see that 30 degrees sodium nitrate. Looks like it's maybe, I'm gonna go with like 97. It's like 97 grams. And this says that it has 70. So that is definitely unsaturated. So it looks like saturated is 97 grams. And we're only at 70. So 27 more. If we add 27 more grams, then it would be a saturated solution because 97 minus 70. Okay. So it's currently unsaturated to get it to saturated. If we tried to add 30, it would then be a super saturated solution. And that last 3 grams probably wouldn't dissolve. It would probably just like stick at the bottom and not dissolve into the solution. Okay, here, let's try another one. What is the solubility of potassium chloride at 5 degrees Celsius? So at 5 degrees Celsius, potassium chloride is right here. Let's see if I can find that line. Right about there. That looks like maybe 28. Oh, sorry, you can see it right there. Potassium chloride, 5 degrees. I'm gonna go with like 28 grams per 100 grams of water. 28 grams. Oh, sorry, there it is. You can see it. Sorry. Okay, there's a whole bunch more questions just like this, but let's just see if we can find another one. Oh, here's another. There's more questions here that you should be able to answer. Let's try one more of these. How about, this is potassium iodide. If the follow, let's find out if these are saturated, if they're dissolved in 100 milliliters of water, which is convenient because that's what our chart tells us all about. Is this saturated or unsaturated? So 120 at 0 degrees Celsius. Let's find out. Whoa. Potassium iodide. Okay. Potassium iodide. Oh, that's potassium chloride, not potassium iodide. Ooh, potassium iodide is way up here. 0 degrees Celsius, 120 would be unsaturated. Actually, yeah, because it's 130 would be saturated. So that's actually unsaturated. Crazy. Okay, so there you go. So that's what the rest of those pages are about. It's really about interpreting this graph and understanding what saturated versus unsaturated means. So I think we'll leave it there, and we will pick up with electrolytes next. So enjoy.